Integration is a way to calculate the addition, and it is basic of calculus. But sometimes it is not easy to do the integration. We are talking about vector field. Vector field is something that is hybrid model of a vector and algebraic equation. Calculus is a game of algebra. So generally we see that calculus is something that infinitesimal small we take here and there, and then it is a science of infinitesimal small width and then height and this. Calculus has nothing to do with infinitesimal small width and then area around it and something. Calculus is pure and pure based upon algebra. Calculus is a way to do addition of an algebraic equation. So if I have something and if I want to do addition, then I can go with, if it is uniform, then I can go with the multiplication also. Multiplication is another way of addition only. Whereas if multiplication is other way of addition, then integration is another way of addition. So integration, we calculate the area. So in integration, we calculate the area. If I calculate the area, then it is nothing but addition only. This is what we have seen. Okay. Now if I calculate the area, then there has to be two sides of the area. Basic thing is rectangle. The width, okay, height and width, height and length also you can say, height and width. If it is height and width, then width is the independent variable and height is dependent variable. So height is also called collection or net collection, whatever, that is based upon the independent variable. Whatever area comes, that is the integration. So integration, so this height can be constant if collection or rate of change, whatever we are taking, is constant, or it can be variation. If height is variation, then it is algebra. Okay, like a person is walking 5 kilometer per hour, then height is a variation. Height is 5 kilometer per hour. That is, this independent component is r. That is constant 5. 5 into 3 are 15 kilometer he has walked. 5 plus 5 plus 5. 5 into 3, or the area. Okay, if he is walking at a speed of t square plus sine t, means that his speed is varying at variation of t. When t is something, then his speed is something. If t is something, his speed is something. If that is the case, then this height is not constant. If t is independent variable along x-axis, then the height is not constant. It is function over t. So height into 2, I cannot do. I can do, means I can say ft, if function over t is the height, then ft into whatever, if I want for 3 hours, 3 into ft. 3 into ft is the integration. What I need is, whatever is the ft, average value someone gives me, then 3 into that. Or I have to do something that ft should be broken down to series of rectangles. If that is true, then we can find the net multiplication 3 into ft. For series of rectangle, people target for the delta t. If it is delta t and consider an height, and it is not the way. Calculus is pure game of ft, algebra. So algebra, you have to keep breaking it till it comes to rectangle. Or as we have said that if I have a triangle, then triangle is based upon rectangle. For triangle, we know the formula. Triangle is like ft equal to t, then integration is t to the power 2 by 2. ft is t to the power n, then t to the power n plus 1 by n plus 1. So like this, we triangle area of triangle is half of the rectangle. So basic is rectangle, but keep on growing and we keep finding the every shapes or every polynomial equation formula. So whatever the formula we get, if we keep breaking till we know the integration, then this is what we do. But calculus is game of algebra. Calculus is not game of infinitesimal small. Algebra keep changing if we change the independent variable. So the calculus, the net integration keep changing. So if I need to integrate a function ft along t axis or x axis, that is called line integral. Means every integration is line integral. Every integration is line integral. Every differentiation is directional derivative. Okay, if I say what is the differentiation of this function, means in 2D I want the differentiation along x-axis by default. If it is 3D, then what is differentiation of 2xy plus x square sine xy what? Then differentiation is along independent component xy plane. XY plane, that is the differentiation we are trying to. By default, it comes to x and y. But differentiation is along direct, always direction. If I don't mention, then it is along the either xy plane or x-axis, whatever. But we can specify that we want differentiation along a particular vector. Like that, if I go with integration, then we know that by default, if it is 2D, the integration is along x-axis. But I can mention that I want integration along any line. This is called typically line integral, but everything is line integral. So line integral along this particular line is the complete word. So if I have a function, algebraic function, and if I am calculating integration, then integral will result in another algebraic function. If integral result in algebraic function and integration is nothing but area, then if I set value of independent component, suppose t, if my function ft is in t, the integration of ft would again be in the algebraic function t. High chance. If that is the case, then keep whatever the integral algebraic equation I have got, keep changing the value of t, then you will get integral value. What is integral value? If you keep changing value of t and you get the integration, what is the integration? That integration is nothing but the area, what we have calculated from the 0. If t is 2, then what is the integration? Suppose ft is t, ft is t, ft is t. So I want from up to 3. So ft into 3 is the net area. But since ft is t, it's not a constant, then 3 into t is the net area. Now t is variable, so I have to go with integration, and t would result in t square by 2. Now I have 3 by 2 t, okay, up to 3. So 3 just remove it. Lower limit, higher limit we remove. We want integration of ft. This is what we call from 0 to 3. Actual answer is 0 to 3, that is the width, that is 3 into ft is the height. So area is ft into 3. Since ft is variable, so we keep 3 aside and just we say we want integral of 3 from 0 to 3. Now ft is t, that is t square by 2. Then now if I keep changing the value of t, it will calculate the area from the origin. Whatever the equation is t is the area from the origin if I keep changing. If I set lower limit and higher limit from there to there in between area, it will calculate. So integration is t square by 2. Keep changing the t. That's how it is infinitesimal small. Not because delta t and here and there. Those can be helping. Those can be helping way to calculate the integration. But at the end, person has to come to algebraic equation backbone. Algebraic equation backbone, he has to come from this side or that side, because like eats tiger eats blood, tiger eat flesh. Okay, if you give radish or if you give some kind of vegetable, then tiger would not survive. He may eat for some time, but he may not survive. Okay, like deer eats grass and vegetables. If you give them a live hen, chicken, or whatever, probably deer will not survive. So calculus will not survive if you not come back to the algebra, because algebra is the food for calculus. Anyway, now we are kind of in a way to do the line to the vector field line integral. So if I have a vector field, so we have talked thoroughly that vector field is a nothing but a vector. Generally, I say 2i plus 3j plus 4k is my vector. If you substitute 2, 3, 4 as algebraic equation, then it becomes a vector field. So algebraic equation and vector hybrid model is vector field. So if I say I have a vector, if I have a vector, vector is from here to here, not here. Okay, if I have a vector and this vector keep changing as I change the independent variable and its magnitude is also changing, then this is someone would suspect that this vector is not a static vector. There is algebra inside it. And that algebra, we can say that if capital F is a vector field, capital F bracket x comma y, it is dependent upon two independent variable x and y. On top, I put an arrow. This is a vector field. Then it is fxyi plus gxyj plus hxyk, where fxy, small f, small g, small h, fxy is function over x and y, gxy function over x and y, and hxy is function over x and y. If I keep changing x and y coordinate, then this vector field keep changing. Okay. Now, if that is the scenario, then what is the kind of this vector field's integration along x-axis? By default, we calculate along x-axis only. But what is this vector field's integration along x-axis? If that is the case, then this vector's effective vector, this is the vector, then what is the effective vector along x-axis? What is the power of this vector along x-axis? That we have to calculate first. That will result in algebraic equation. Then it is generally, I say, football match example. Like I think this is third time I'm repeating that people kind of in India and in some one province in India where I come from. So there people, they don't know English, means Hindi is their mother tongue or whatever it is. So people, they remember, means they see the book and they try to mug up the essay, and essay they thought that it would come in examination is football match, and they everyone mugged up football match when they went to examination. Then essay was journey by aeroplane, and everyone came out of the examination hall with a pale face because they did not remember the journey by aeroplane essay. They did not mug up the journey by aeroplane. Now, but one person is happy, one student is happy. Then they asked, how you are happy? Why you didn't tell me that this is the essay that is expected? We would also have remembered. We also would have mugged up. Then he said that even I was not knowing that there will be journey by aeroplane. But somehow I changed the path of this essay finally to the football match. Means journey by aeroplane. Aeroplane is going and everything is nice. Suddenly some problem in aeroplane and there is the emergency landing of the aeroplane, and then nearby football match is going on, and then he wrote full essay about the football match. So in calculus, either it is vector or it is infinitesimal small, or it is here in Washington, or it is Kinshasa, or whatever. At the end, you have to come to algebraic equation. Better quickly you come to the algebraic equation, because if lion need blood, then it's a bad term, blood, but that is true. Or a deer need grass. If deer need grass, then algebra needs calculus needs algebra. So if I have a vector field is nothing but a vector where each component of vector is algebraic equation. Okay. Now if this is the vector and this is the x-axis, this vector's integration I want along x-axis. Generally, algebraic equations integration we do along the x-axis. So if this is x-axis and this is algebraic equation, then its area, what it covers along x-axis, that is the integration. But if this is a vector which has direction, then what is the vector's effective vector? What is the vector's presence along this axis? If it is x-axis, then along this axis. Whatever comes, that will be algebraic equation, then football match. After that, you can start. So if I have a vector which has I component, j component and k component, just take out the I component because we want along I axis, that is an algebra. Then start doing the integration. And then lower limit to higher limit or wherever you want the line integral. Or if you want if you have a vector field capital F and you want line integration along any vector, not I vector is x-axis, any vector u. If there is any vector u, this is the vector, this is the vector u, and this is the capital F. If this is the capital F, then F presents along the u vector. This is the effective vector of F along u vector. Then do the integration. So effective vector of f along u vector is nothing but dot product of f vector with unit vector of u. That will take out the f's essence along this vector. That essence should be algebra because at the end you are coming to integration. So once algebra is comes, then du. So vector field f dot use, if this is u vector, use unit vector. Vector field f dot use unit vector. Then f's essence along the u will come into the picture. Du. Here dx if it is I vector. Okay. Since I vector. Since vector is kind of is vector is generally it is dissociated in I vector, j vector, I component, j component, x component, we can take out in exactly the I component. But if I go with the formula, the vector field f vector field f dot I is unit vector, dx. Okay. Or if I take out that side, then vector field f dot dx vector, I came this. Or if it is vector field f dot unit vector of u du, unit vector of u, if you take that side, then it becomes vector field of f dot du vector. Then it will at the end it will result in an algebraic equation. Then you can do integration. Nice one. So people learned now that how to change aeroplane by journey essay to football match essay. Means if I have vector field also, how to convert it to algebraic equation and do the actual integration and place the limit. But people are even more smart. So that's why the independence in path comes into the picture. If I have vector field capital F, if I have vector field capital F, then what is its integration along a line? Along a line from point A to B. Like I gave an example, like if it is x-axis and this is y-axis, then there is a line intercepting x-axis and y-axis. If this point is A and this point is B, then what is the line integral of any vector field along this line from A to B? Okay, people are even smart. What people saw is who has invented, I have utmost respect for it because this is something that no one would have dreamt it the way he had thought. But we will see many things people have placed in mind. Very beautiful mind. Okay. So if I have capital vector F capital F dot D U is the line I am saying. If this line I convert into a vector, that is du vector. Now, if I do line integral, I am not placing the limit now. From A to B, I am not placing the limit. If I f vector dot capital F dot du vector, if I calculate this line integral, what is line integral here? U vector, I can I can represent it as xi plus yj, any xi plus yj. If that is true, then d of xi plus yj will result in dxi plus dyj. Here I have capital vector F. Capital vector can be represented as F1, first component, F1i plus F2j. If I do dot product, it will become F1 dx plus F2 dy. That is algebraic equation, whatever. Now, if that algebraic equation, if I calculate and then I find that this is another algebraic equation, small f, that is a function. Then what people saw in some scenario, this small f, capital F dot du, both are vector field. U is also vector field and capital F is also vector field. Small u. If I do integration equal to small f, that is the potential function generally people call it. Whatever the potential function I receive, okay, that potential function in some case it is dependent only upon capital F, not on the U, not on the line on which I want the line integration, only on F. Amazing, man. Amazing. If I do capital F dot du vector equal to small f, then f is only dependent upon capital F, not on u at all. This is called path independent. Means vector field is vector. If I want line integral of vector field, then it is not dependent upon the path of the u. It is only dependent if that full result in f, then I can substitute this with f mathematically. If capital F dot du vector is small f, that is potential function, the full I can replace with f. So integration of f, not dx dy, means I have to just place the limit from a to b in the algebraic equation of f, small f. If that is the case, then people saw that this small f is only dependent upon the capital F, not on the du. This is called f is now path independent. Only thing that matters is lower limit and higher limit, two end of the integration. So path independent. How people saw that is if if they able to find the algebraic equation f. First is that you have to find the net algebraic equation f. If they are able to find the net algebraic equation f many times, okay. So if I have capital F, I'm not talking about u. Okay, if I have only capital F dot du, capital F dot du vector. Just think about capital F. If capital F, if I do integration of the capital F, if I would rephrase it. Okay, so consider that there is a case that capital F dot du vector results in small f algebraic function. If I calculate gradient of algebraic function f, then people saw that is equal to the vector field f, capital F, capital F dot du vector equal to small f algebraic equation. I'm not talking about the limit. If I calculate gradient over small f, gradient means df by dx I plus df by dy j, that is exactly equivalent to capital F vector field. If that is the case, then I don't need du. This is how people saw. They hinted in their mind. If that is the case, then can I get this small f directly from capital F? If I'm able to get it, then then this is path independent. I don't need you. I would repeat it. So if I have capital F vector dot d u vector. If that integration results in vector in algebraic equation or potential function small f, then gradient of small f, that is df by dxi plus df by dyj, this is the gradient vector. This vector is same as what is the vector field f. If that is the case, then can we get the potential function small f directly from f? If we are able to get it, then this integration is not dependent upon du at all. Because whatever full integration, what we were getting result as potential function of small f, same as small f, I am directly getting from the capital F vector. So if that is the case, then since it is not dependent upon u, means not on the path, so vector field is path independent. Then full f dot du, you can just take it out, and whatever f you have received from capital F, just place it there and set the limit from one end to another end. That then it is path independent. Now if that is the case, then you have calculated the f dot d. Integration is difficult. Generally, people see differentiation is more predictable, more easy to calculate than integration. When people go for integration, people try to do antiderivative. What would have been the function for which derivative is this? That is the opposite is the integration. So integration is difficult. So if I do capital F dot du and u du, if I know capital F is path independent, then if I do capital F dot du and u path is a straight line, immediately I can calculate the integration. Okay, someone is saying, can you calculate line integral of this vector field from this point to this point, and connecting line is of equation e to the power xy plus sine x plus ln to, extremely complex. He is giving the path from one point to another point and asking to calculate the the line integral. Now just check that capital F, for capital F, can we come with a algebraic equation potential function small f? If it is possible, then it is path independent. Just make a straight line, or if you have calculated the potential function, then that is the integral. Just set the lower limit and higher limit. So people got rid of one way of doing integration, because if they come to know that there is a potential function exists, path independent, then at the end only you have to calculate the potential function. If you are not able to calculate the potential function, but if you know, this is the case number 2. If I have a vector field that is simple, and the path along which I need line integral that is too complex, then for this vector field f, if I am able to calculate a small f, that is a potential function algebraic equation, then immediately I can say this vector field is path independent, not dependent upon any path. So I can take out the path at all, and then this is the potential function. But what about in some cases when you are not able to calculate, someone is not able to calculate the potential function f? It doesn't mean that potential function f do not exist, but somehow it is difficult to do the integration. Okay, if difficult to do the integration, then how I can find that it is path independent? But if I able to find out that it is path independent, then the du f dot du, I will take a straight line, then I'll do dot, and then I'll try to calculate the integration. It is simple, because no, if it is path independent, for capital F I am not able to find the potential function due to my limitation in the integration, or integration, whatever, I won't say integration is limited, but whatever the way that has been shown as far as now till now, for the integration, those methods are not sufficient to calculate this integration. Then what is the other solution? Now we will talk about this. So if I have other solutions available, That would prove that this capital F is path independent. Then capital F dot du, u is the line curve that has very complex equation. I'll change, throw it, I'll change it to straight line, and then I'll do dot product, and then net. I'll try to calculate the integral. Dot product is easy, right? Means if I have a line equation y equal to x with slope 1, or if it is 2 point straight line, slope 2, 3, whatever it is, then what is the net integration we come up with? That is f1 dx plus f2 dy. Capital F1 dx plus capital F2 dy. This is what we saw. Now, if y equal to 4x, then dy equal to 4 dx. So there y dx, y dy, the dy I'll replace with the 4 dx, and y I'll replace with the 4x. It will become 16x dx, and here x dx, 17x dx, x square by 2. Okay, I mean that is f2 dy. So whatever f2, so I took xi plus yj as a vector field, xi plus yj, then x dx plus y dy. Otherwise, f1 dx plus f2 dy. Proceed in same fashion, and it will be simpler. So now idea is that, can, if I am able to, from capital F, if I am able to find the small f, then anyway I have the result. I know it is path independent, and then I have the result also. But somehow I am not able to calculate small f, but still I am curious to know that it is path independent or not. If it is path independent, then path I will rephrase to some straight line and calculate the integral. What is another way of being path independent? If it is path independent, then it would not vary, depend upon the path, only beginning point and end point. Beginning point and end point. Take a line, take a line and calculate the integration from A to B. Then calculate the integration from B to A. Then it makes a closed loop. A to B and B to A, if you add it and it becomes 0, then it is path independent. If it is path independent, if I have one point and another point, then just I need to worry about these 2 points, and then my work is done. If this point is again come back to this point only, so integration from this point to same point, obviously it would result in 0 if it is path independent. If I want calculate from A to A and it is not dependent upon the path, so integration has nothing to do with the path, then it would result in 0. Otherwise, it won't result in 0. So someone would say that if I take integration A to A, certainly it will result in 0. It will not result in 0, because if I divide this path in two sections, from A to B plus B to A, then A to B will be different and B to B, A will not be negative of it. Since it is path dependent, then it will not be 0. Now, if I convert the U curve line that was in high class polynomial exponential into straight line, A to B and then B to A, if we add, and if it results in 0, then it is, we consider it as the path independent. Okay, or we take path of a circle and then we try to do it. So once we see that line integral of any line integral of any vector field is 0, then we immediately I can say in a closed path. In a closed path, if a line integral is a 0, closed loop, it is 0, then it is path independent, provided the vector field f is continuous. If there is a closed region from here to here, there is a region it makes in between. In that region, if vector field is continuous, there is no hole found. Like vector field is minus yi plus xj divided by x square plus y square. At x comma y equal to 0 comma 0, the vector field is not defined. In that case, the closed loop principle that it will result in 0, we cannot. Vector field must be continuous. If I take closed loop, then full region inside the closed loop, vector field must be continuous. There should not be any hole out there. Then now I can say it is actually path independent. If it is path independent, then if I want to calculate vector f dot du, then you can take whatever you think that after doing dot product, it will come to a situation where you can do the integration. After that, anything that is in u, you don't bother. So that results in path independent. What can be other way? Now consider that I have vector field f. Vector field f. Vector field f is can be represented with gradient of potential function small f if it is path independent. Okay. Vector field vector field f can be represented as gradient of a potential function small f, where small f is result of the net line integral. So if I do f dot du vector, whatever comes in, that is small f potential function. If small f is the potential function that results in, then gradient vector of the potential function small f is capital F that we have seen. Now, small f, we are talking about small f. So, small f means df by dx. df by dx is capital F1, first field of the vector field. If gradient vector of small f, if potential function that is small f, gradient vector of a small f result in capital F, then capital F can be represented as F1i plus F2j in 3D equal to small f df by dxi plus df by dyj. Now f1 equal to df by dx, f2 equal to df by dy. f1 and f2 are vector field capital F, and df by dx and df by dy are potential function result, that is small f. If that is the case, then what is now small f we are talking? df by dx I know. Then what is d2 if I differentiate it with y? Again, df by dx if I differentiate with y, then it will result in d2f by dx dy. dx dy is area, not a line. So d2fy dx dy. Now we had another one dfy dy. If I differentiate with x, earlier we had df by dx, I differentiated it with y, then it resulted in d2fy dx dy. If I have another component, that is j component, that is df by small f, df by dy, if I do differentiation, then it would result in d2f by dy dx. Both are same. d2f by dx dy is same as d2f by dy dx. Both are talking about the same area region. If that is true, then d2f by dx dy minus d2f small f d2f by dy dx equal to 0. Okay, if this is 0, then if it is path independent, then f capital F dot du vector in a closed loop is also 0. So these zero are they are related. We will talk about it under Green's theorem. There is another person comes into the picture, and his name is Green, and he is really green, means something that he has contributed to the power of calculus, means amazing, mind blowing. Anyway, now we came to now a formula that small f d2f by dx dy minus d2f by dy dx is same, so minus would result in 0. If that is the case, then That we'll see. What is d2f by dx dy? If df by dx small f, if df by dx is capital F1, then d2f by dx dy is capital F1 by d of capital F1 by dy. D of capital F1 by dy. Now another one is d2f by dy dx. That would result in d of capital F2 by dx. One is d of capital F1 by dy and one is d of capital F2 by dx. Now both are same. This is what we saw for the for being a path independent. If it is path independent, then capital vector F field can be represented as gradient of potential function small f. This is what we saw. If gradient of vector small f is nothing but df by dxi plus df by dyj small f. Now df by dx, if I differentiate again with y, then d2f by dx dy. If I another one, if I differentiate with x, then it will become d2f by dx dy. dy dx dy both are same because they represent an area. If they are same, then here if I take out here on left side, that is capital F, then d of f1 by dy and d of f2 by dx are same if it is path independent. Now we got another way to calculate that it is path independent or not. How? That is d of f1. If I have a vector field, if I have a vector field equation, then it has component as f1 and f2. d of f1 by dy and d of f2 by dx, if both are same, then it is path independent. Whoever has thought about it, okay, then he is more than genius, especially to people like us who fear doing integration. Integration is something that I personally start sweating. Okay, differentiation where chain rule comes into the picture, and quickly through chain rule you try to boast that you can differentiate anything. But chain rule in integration is there, but it would result in a really a chain, infinite chain, many times. So here, if I if there is a way through differentiation, if I am able to find out that it is path independent or not, then it is great. And then if it happens in this fashion, then if I need to do the line integral of vector field f, capital F dot du vector, then u I can take any straight line and calculate the capital F du vector and then set the limit, you get the line integral because you know it is path independent. How you know path independent? Consider it is path independent. If it is path independent, then capital F can be represented by a potential function small f. If that is the case, then gradient of a small function small f is nothing but capital F. If that is true, then df capital F dot du full integration can be represented as small f. Again, capital F dot du, where capital F is vector field. Capital F dot du, u is the line vector, represent a potential function small f. But gradient of small f is nothing but capital F. This is what is seen. So anyway, now that if consider that consider that capital F through capital F, I am able to get the small f. Through capital F, I am able to get the small f. If that is true, then gradient of small f is capital F. If that is the case, then this is path independent. If this is path independent, then capital F equal to df small f. Capital F equal to df by dxi plus df by dyj. If that is the case, whatever the potential function I have received through capital F, okay. Now capital F can be represented as f1i plus f2j. On that side, small f, it is df by dxi plus df by dyj. Now, if that is true, then f1 equal to df by dx, f2 equal to df by dx, where f1, f2 in capital and df by dx, df by dy in a small, that is potential function. If that is true, then a small function d2f by dx dy and d2f by dy dx both are same. If both are same, then d of df by dy and d of f2, d of f1 by dy and d of f2 by dx are also same. If they are same, then their subtraction would result in 0. If that is the case, then this capital F is path independent. If it is path independent, then u through which I am calculating the line integral, now it is in my hand what I take to calculate the integral. Or okay, means I am getting rid of calculating the potential function through capital F, through integration. That I don't want. So I just want to prove it is path independent or not. If I have capital F, take out F1 component and F2 component. dF1 by dy and dF2 by dx calculated and see if it is same. If it is same, then it is path independent. Then do whatever you want to do. But there are caveats. It's not straightforward. The capital F. Now, if it is path independent, then for any closed region, if I take like a circle or any closed region, if I take in that closed region, okay, the capital F, that is vector field, must be continuous in the region. There should not be any hole. So for any closed region, then line integral should be closed line integral should be possible. So capital F generally it should be continuous. That is required. Second is its single derivative. Capital F single derivative that we are doing. Those derivative should also be continuous. If that is the case, that then we can say that df1 by dy and df2 by dx, if they are same, then it is path independent. Once it is path independent, then integration what you are doing capital F dot du, now it would become very simple. People like us who put kind of much concentration here where integration we feel it is difficult. So path independence we saw through three ways. One is if I have capital F through which if I do some integration like f1 dx, we showed in the last session, if I do some integration and if I try to find out a small potential function f, capital F to a small potential function f, if I am able to get the small potential function f through some way, or from this full world of algebra, if I am able to search a potential function f for which gradient vector is exactly as capital vector f, then it is path independent. If it is path dependent, then small f calculation is not possible. We gave example of vector field 2xyi plus xyj. For this vector field f, calculating the potential function is not possible. Last session you can see the way. Now, anyway, so if I am able to calculate the potential function f from capital F, then it is path independent. Or in world there are billions of functions. If I am able to search a function for which gradient vector is capital F, then it is path independent. One way. Another way is path integral is capital F dot d. If this integral for in a closed loop, if it is 0, and in that closed loop vector field f is continuous, then it is path vector field f is path independent. Or if vector field f is continuous in a region in the sense, you remember that we did dx and dy, differentiation with dx and dy. Dx and dy, it sums up to an area. So in that region, if capital vector F is continuous and it is differentiable, each component of capital F, that is F1 and F2, is differentiable and differentiable in that region, again it is continuous, then if df1 by dy and df2 by dx are same, then it is path independent. Okay, but can you see this? We never check that path f is continuous or not if I am able to get the potential function small f. This check is only for closed loop 0 and then df1 by dy and dff2 by dy calculation only. If I have vector field f, for that I am able to find the potential function f, that is enough. Then your vector field f is continuous. Doesn't matter it has a hole or it does not have hole. Getting to the small potential function itself is very difficult. So three ways in checking that vector field f is continuous or not. Then what is the way that I can say it is not continuous? It is not continuous because potential function f do not exist. Okay, and if do not exist, that is the one sign. Second sign is closed loop integration, line integral is not zero, another sign. And third sign is df1 by dy and df2 by dx are not the same. Then it is certainly it is path dependent. Certainly it is not path independent. Okay, so that is the scenario. We will see more on it. Then we will proceed on the three-dimensional parametric vector in the vector field calculation. So that we will see.